Okay, today we are kind of launched the series of the satellite and meteorology satellite environmental remote sensing. Welcome you all in here during the pandemic. Today, the first starter of this series will start by Tim Schmit. Tim Schmit is a researcher at for the NOAA NESDIS star. Okay, and as you see, his affiliation is on the slides. And he's kind of my mentor when I was studying in Wisconsin. And everything I know when I was young, actually that's more than 10 years ago. Actually, he gave me a lot of guidance, and when I don't know anything, he will be very nice and put down all what he's doing and talk to me for a few minutes. That's a lot of help during my study when I was in Wisconsin. As usual, he is in the picture, and it's midnight. Not midnight, it's about 9 p.m. in the 90 Central daytime at this moment. So
yes, thank you for that warm introduction. It was great to have you for your time in Wisconsin. As you know, I really like talking about GOES. I could not decide what to talk about, so I decided to try to talk about everything. So yeah, there I am in my fancy car. Yeah, we can stay with this outline. So the outline is very simple. A little bit of the history of the GOES. In fact, you know, and then most of the time spent on our current constellation, GOES 16 and GOES 17, and then a little peek to the future about a possible advanced geostationary sounder. Most important part will be the question and answers part at the end that either, you know, put in the chat or send me emails after the fact, whatever works for you. So yeah, let's go on and do the next slide. Yep. So, you know, Madison, Wisconsin has been known as the birthplace of satellite meteorology, and that's because of Professor Werner Suomi's work that started in the late 50s. So for example, here he's has a satellite that's measuring the heat budget of the atmosphere. And so Wisconsin satellite legacy can be traced back all the way to the late 50s. Go on to the next slide. Now this image was not made in the 50s, but it was using data that was recorded. And as hard as it is to believe, you know, we're still trying to understand the relationship between, say, the outgoing radiation, you know, versus cloud cover. And you can see here much less radiation over the low of where there were clouds. Here's data from early April 1960. Next slide. But, you know, we're really here to talk about the geostationary orbit and the imagers and the instrumentation. That really started with a proposal that Werner Suomi wrote in 1964 to say we should put a cloud camera up on this advanced applications technology satellite that NASA was going to launch. So the proposal was in 1964, and the data from space came in late 1966. So launched in December 6th, and you can see the image there, December 11th. It had one visible band. Next slide. So they weren't even sure what to call this new thing. So for example, maybe it was a weather eye or a multi-purpose moonlet, because of course this was a new orbit to many people. Next slide. So that was ATS-1, and then it was quickly followed by ATS-3 in 1967, where it wasn't just one visible band, but had 3 visible bands in the red, green, and blue, so you could make true color type images here. So you could quickly see GOES, you can see South America, North America, the Northwest, and Africa to the east. But this really started the world of geostationary imaging in more than one spectral band. Go on to the next slide. So, of course, that was the, you could hit just spacebar one time. So that was the experimental forerunner, ATS, and then there was SMS. But the GOES, or Geostationary Operational Environmental Satellite, started in 1975. And you can see here the number of generations. So, for example, GOES 1 through 3, you know, were spin stabilized. GOES 4 started to have vertical profiling with very broad spectral bands. A big improvement came with the GOES 8 series. We went to the 3-axis stabilized spacecraft. And so we could get better signal to noise. GOES 13, 14, and 15 were really clones, different spacecraft, but similar instruments as earlier. But the big step came up in the GOES R series. As you may know, we give them letters when they're on the ground. So GOES R, once it became up to the geostationary orbit, then it got its numbers, if you will. So GOES R became GOES 16, GOES S became GOES 17. Next slide. So here's a little bit more detail, again, going from the GOES, where we had one visible band and one infrared in the GOES 1 era, to the you know, GOES R, where we had where we had 16 total spectral bands, a geostationary lightning mapper, but no longer an advanced sounder. The next slide. So here was an example from GOES 14. So this was before, this was in preparation for GOES R. GOES 14 is a spare satellite that we have right now. And so it shows on the left a glimpse of what we would get with ABI with its 1-minute mesoscale imaging, as opposed to the, you know, more or less time resolution on the right. Of course, ABI had other attributes improvements as well. But again, this gave us a glimpse to how quickly things happened in the atmosphere. Going to the next slide. So that was with the visible bands, and a similar example, again, using GOES 14 with infrared. Yeah, if you go back one slide, it might take a minute to load. Slide 11, yeah. So there was an enhanced V, or a thermal couplet in the cold clouds there, and anyways, you could see it sooner with obviously the 1-minute data versus the 15-minute data. So next slide. So I'm again happy to talk about a lot of different questions of what came before the GOES R, but GOES R was the big real game changer. So you know, we'll talk mostly about the ABI. As you know, there's also this geostationary lightning mapper, which gives you total lightning. There's also space weather instruments, which I won't talk about. Mainly concentrate on the improvements of the advanced baseline imager, spatially, temporally, and spectrally. Yep. So yeah. So here shows the continuity. Yeah, we can go on to slide 13. So the O in GOES operational, again, so continuity is really a key for us. So here's just thumbnails from GOES 1 in 1975 to GOES 17. We made GOES 16 and 17 bigger because they're better sensors. But again, first of all, we have continuity. Going to the next slide, we also have a lot of improvements. So here's just a snapshot of our current constellation. We have GOES 16 as our operational E satellite. at 175 west, and we have GOES 17. GOES 17 as our west satellite at 137 west as part of the global constellation. And then we have a number of legacy, like for example, GOES 15 as backup satellites. Going to the next slide. Again, GOES-R does more than the Advanced Baseline Imager, but that's what I've been working with. We started in 1999 getting ready for ABI. So that's what we'll talk about mostly. Go on to the next slide. So in a snapshot, you know, the spectral coverage from our latency imagers improved from 5 spectral bands to 16, or basically a factor of 3. The spatial resolution improved for the visible band from 1 to half a kilometer, or in the infrared, approximately 4 kilometers to 2 kilometers, and much more frequent imaging. So for example, instead of getting the continental United States every 15 or 30 minutes, we got it routinely every 5 minutes. And we have these mesoscale, or 1,000 by 1,000 areas every 1 minute. Or if we looked at the same place, we could actually see them every 30 seconds. Next slide. So, you know, as I mentioned, when I started working on ABI, it had 8 spectral bands proposed, but a whole lot of uses. So we were able to suggest some new bands. And as I said, we got it to improve from 8 spectral bands to the 16 over the years. Go on to the next slide. This lists out the central wavelength of the 16 bands that we have, and some of what I'll call band champions, or some of the people that suggested that we should have on here. Of course, some of them go back to Vern Sumi in the early days. Our friends in Europe, if you look at band 8, had the first water vapor in geostationary. So again, I like to tell people, sometimes people think satellite data magically is beamed down from space. Obviously, somebody had to think of a band and its characteristics and build it and launch it, etc. So next slide. So here is just some thumbnails of some of our first light imagery from ABI. So 2 bands in the visible, the blue and the red spectral regions, 4 in the near IR, or think of them as near visible, and 10 in the infrared. Go on to the next slide. Then this really just shows pictorially there the 2 visible bands, the 4 near infrared. We have a number of infrared window bands. Those are kind of colorized the red there. And then another number of bands that might be cooler due to water vapor absorption, bands 8, 9, and 10. Or a band sensitive to ozone absorption, or band 16 CO2. So we go on to the next slide. And then you can just step through these. These are the 16 bands of a case there, showing the, you know, here's a fire, and you could see it there in some of the hotter spectral bands there. Yeah. So again, the products that get derived are from these various. Yep. And there's the arrow kind of shows where it is there. So again, all the information that we derive is from these spectral bands. Go on to the next slide. So as I said, we've got a blue band, a red band. That's one that we had at Heritage, a band sensitive to vegetation, a band very sensitive to cirrus, although it's also sensitive to upper things, a snow ice band, or maybe we should have called this the glaciated band, because it's also good for cloud top, looking at if it's water, liquid water, or frozen. And then a band for cloud particle size. So next slide shows this spectrally. what I just said. So, and then we've added on the instrument response functions. So again, the blue band, the red band, and the near infrared bands. You can see band 4 is somewhat unique there in that it's kind of in the center of an absorption feature. So that kind of masks out the surface. So that's why it's more sensitive to see upper level features like cirrus. Next slide, zooming in on the transition to vegetation there around 0.7 microns. So you can see how if we compare these two bands, we can see that one is more reflected to vegetation versus the other, where they're kind of equally reflective to something like dirt. You can see that doesn't show that spectral variation. And of course, this is important if you're interested in a burn scar or vegetated health. On to the next slide as we go to the now the infrared. As I mentioned, we had 4 bands on the previous imager, and so we traditionally had the 4 micron. We still have that, but instead of having 1 water vapor band, we have 3 water vapor bands in the mid-level, and including the 7.3, which is also sensitive to SO2 associated with volcanic eruptions. Then we have a cloud top phase band at 8.4, which is good because we used in night because it's an infrared band. I mentioned this ozone sensitive band at 9.6. And then instead of having 1 window band, we have 3 window bands that are more sensitive to moisture and a 13.3. And obviously these are the same spectral bands that are on the AHI, Advanced Himawari Imager. Go to the next slide. So same deal. Now here's theoretical atmosphere, how it would emit in the infrared. So temperature decreases as you increase on the y-axis as we go across increasing wavelength. Hit the space bar once, you should then see the go to the next slide. You see now we've added the impulse response function. So you can see where we do observe data and where we don't. So for example, you can see the water vapor bands there between 6 and 7 microns. You could see, for example, around 8.6, it's cooler due to ozone absorption. And then as we get to the longest wavelength, 13.3, etc., it gets cooler again to CO2. But to explain that more, if you go on to the next slide, we've taken this theoretical atmosphere and taken out the individual atmospheric components. So for example, the blue, the dark blue, is if the atmosphere had no moisture. And you can see, yes, there's a big signal there, a big difference. So basically, somewhere between 45 and 65 degrees colder when you put water vapor in the atmosphere. But you can see you have water vapor absorption really through the whole part of the electromagnetic spectrum here in the infrared. But you can see, for example, if you look at the 2 gray areas at 7.5 and 8.7. So you can see those 2 spectral signatures. So again, you can play this off against other bands that don't see SO2 to get an estimate of, for example, SO2 in the atmosphere. And there are other atmospheric major gases and minor ones listed there. So if we go on to the next slide, here's a, putting some of these images together as kind of a sandwich approach. So the infrared and the visible. Here it's kind of shown in a storm relative of a hurricane near Florida. So again, you're getting to see some of the fine scale detail from the visible, but the temperature color coded from the infrared. This is just one of the many ways of how you can start to combine data multispectrally. To go on to the next slide, One of the most popular ways to combine things is kind of in a true color image. This is over Alaska, and here's a showing off some of this 1 minute time resolution imagery or mesoscale locations. And you can see in the center of the frame there a volcanic ash plume there. So again, you can use things in the infrared at night, but during the day, this is higher spatial resolution. And I guess best is to combine all the information together. Go on to the next slide. So there's a lot of imagery examples out there, but most importantly, or also equally importantly, are these derived or level 2 products. So not only the cloud and moisture imagery, but when you go into quantifying cloud top characteristics, be it the pressure, the height, or the surface features, the land surface temperature, the sea surface temperature. We also can derive total perceptible water or lifted index or atmospheric stability, snow cover or other cryosphere products. And this is just the ones that were kind of thought of well before launch. There are always new ways to use this improved data. The next slide. This is a table form of what I said. So you can see there's, the radiances, which we'll call a level 1B product, the kind of a base foundational product, and then the number of level 2 products. That's where we talk about imagery, cloud mass, stability, a lot of the things I talked about. If you hit the space bar one more time, we'll see there are some new products that are coming online. Have to do with for example, cryosphere. If you maybe have to hit the space bar, there it is. So yeah, so these are the Pathfinder and just some new products associated with, for example, ice concentration or motion. Go on to the next slide. They're just ways to combine these. So here we've color-coded the total perceptible water in the color, so red being more moist to the south there, and some of the dry plumes there to the north in the browns and blues. And then the cloud height is just in grayscale with the lighter clouds being higher. So again, just a different way to visualize these data. Go on to the next slide. I have a page with a lot of links associated with GOES-R. It has links to imagery, data, calibration, software, training, education, and some links to some of these level 2 products. It also has information about some of the space weather instruments and the geostationary lightning mapper. So again, I like to think of that as a good spot to start, either if you want to look at imagery or you want to get some data, both out there, for example, on the cloud, so you can get data pretty easily, or what you might want to do that with various software, publications, etc. So if you go on to the next slide, one of the type things that's on this page, for example, is it discusses the naming conventions. So you can go out on Google or Amazon Cloud and grab a file. Well, what does that mean? So OR meant it was operational. So the instrument was the ABI. In this case, it was level 1B class. Radiances, specifically from the full disk. The different scanning modes. So this was mode 4, channel 13 from GOES 17. And it started on this example is from 2019 at 0Z basically. And then some examples of when the time, the ending, so the starting time, the ending time, and then the creation time. and it reminds you it's a NetCDF. So, and again, so how to read the data, some software, etc., if that's where you're at. Go on to the next slide. This is from one of these files. It's called the Product Users Guide, but there's a lot of information out there. So again, with more detail of not only the file naming conventions, but what each variable within the NetCDF means. So next slide. And when we get to the question and answers, I'm happy to take any questions about, like I say, early goes, current goes. But with this opportunity, I just wanted to talk a little bit about this geostationary, our next generation plans, which hopefully will have an advanced sounder. Go on to the next slide. The core capabilities, of course, it will have an infrared. I should say this is currently just planned. Nothing is been approved yet, but the planned core capabilities will have an imager similar to the advanced baseline imager with some improvements and some other instruments as well. One of the things we're looking at is improving the spatial resolution of the 3.9 micrometer band. So the top along the Texas coast shows two hot spots. The one's very obvious, and then one to its west, and yet you can see that. And when we got ABI, we said, boy, look how good this is. But the bottom panel was an example from MODIS, and is an example with 1 kilometer. And, you know, so it's easy to pick those out. They're hotter signatures. It doesn't get as blurred. So that's one of the planned improvements with the imager and this GeoXO program. Go on to the next slide. There's a number of instruments that are being considered and are recommended capabilities, and one of these advanced infrared soundings. So what's there on the right is the weighting functions, or the contribution functions, if you will, for moisture for the long wave band of this advanced imager. Go on to the next slide. So why do we need this? We have an imager. The imager gives us these very pretty pictures. And the real reason we need this is, well, there are a number of. One, the imagers really average out important vertical information. The ABI was designed to operate in concert with the ABS, Advanced Baseline Sounder, but that didn't make it to space. Weather forecasting is the main thing, both short-term nowcasting and also forecasting applications for numerical weather prediction. But having an advanced baseline sounder allows for additional applications or improving imager-only products with the information. There's also been some work with showing the economic impacts, and of course, this would be part of the global constellation. So if you go on to the next slide. I wrote a paper in 2009 that really summarized some of these potential benefits of the what a advanced baseline sounder or advanced sounder would give us. And really the only thing that's changed since then is the case has only been strengthened with experience from many instruments and sensors. Next slide. So, and this just shows you how the sounder has a lot more vertical information. So if you look on the left-hand side there, the green line, it would be the information possibly from this sounder, and with all that information in it, where an imager would just would really average over that important vertical information. And that's shown on the right-hand side as well. If you look at the number of pieces of independent information, sounder, or the middle two bars, gets closer to a RAOB than the right one, which is an imager-like. And the colors are for temperature and water vapor. Go to the next slide. So here's just showing that same point again. If you look, for example, on the left-hand side and you're interested in low-level temperature, that online-offline absorption feature is really the key, but the imager just averages over it. Next slide. And again, you want the high spectral resolution to give you improved higher vertical information. So the GOES would give you something like the red curve, which is kind of just the mean value, in this case, moisture over the Gulf, which is fine, but we already know that. And this is a kind of an old case from AIRS, but that's okay. It shows that the green, or the AIRS, shows low-level moisture, then some drying around 800 millibars, then some mid-level moisturing around 650, and then it dries again. And that's been borne out by the drop wind sonde. So again, if we have this from GEO, you can get it more frequently than with the LEO sensors. Next slide. And you know, LEO's sensors are great, especially for global NWP, and they have really led the way for impact in showing improvements to global NWP. But the idea is if we have them in GEO, we get a higher time resolution. Next slide. So again, there's applications in forecasting. And I know you're going to hear more from Dr. Smith on this topic, but you know, LEO has been used for years, and that's good. But again, sounder can not only give you higher time resolution, but then the clouds can move, and that'll also improve the yield, as will finer spatial resolution. Next slide. We've you know, so there is advanced geosounder up there now, GEARS, and looking at one case has shown the typhoon improvement by over 40% for Typhoon Maria. Next slide. We've done some hybrid OSSIs to basically simulate what hyperspectral GEO would show. And the bottom line is, you know, improved moisture, temperature, winds, and precipitation. And the improvement from winds wasn't even assimilating this winds. And I think that's an area of research to show even more impact. On the next slide, I mentioned about how we can have improved imager products if we have a sounder. And here's an example on the right of showing much improved cloud height, especially for thin clouds, when you have a sounder, hyperspectral IR sounder, versus without it. Next slide. And then we'll show how we improve. So the sounder data can improve imager-only products, but higher spatial and temporal resolution from the imager can help the sounder, for example, understand what's in their sub-pixel characteristics. So next slide. And then, of course, new areas as well. One I point out here is surface emissivity, which means then maybe we can improve and assimilate more imager data over the land. And again, we'll come up with new areas as well. Next slide. So we've looked at the economic impact, and even just looking at 5 economic sectors. I think these are in 2009 dollars. They showed an impact of over $4 billion US. Next slide. And of course, we're part of the global constellation as well. having a ring of these in the geo. I mentioned Vern Sumi, the father of satellite meteorology, said in 1985 of how the increased spectral resolution in infrared region are feasible and would be highly useful. He said that in 1985. So anyways, let's go on to the next slide. We'll get to the summary part. So next slide. So in summary, you know, we've had a lot of improvements over the years, but really the big improvements have been with the advanced baseline imager, in this case, the number of spectral bands. Go on to the next slide. Big improvement in the spatial resolution, again, with the advanced baseline imager. We go on to the next slide, and then the coverage rate, big improvement with the advanced baseline imager. Go on to the next slide. So, you know, we've had our big game changer, if you will, on the imaging side in geo. So over the US, we're still waiting for a high spectral IR game changer, which hopefully will be part of the GeoXO program. Go on to the next slide. I'd like to say that there's 3 groups of users of satellite data: people that are using it directly, and hence they know it, or they're using the products. And so they may know it, or maybe it's a blended product, or maybe it's part of users and services from the National Meteorological Center, for example. So basically everyone. The space bar. Going to the next slide. Yep, basically everyone. So if we're going to the next slide, just a little bit more information out there on, you know, looking at just the hurricane applications, maybe over $9 billion over the life of the instrument. Go on to the next slide. Again, you know, we continue the critical continuity. There's large societal impacts, and the advanced baseline imager is improved, and improved. Now, following slide shows, you know, BAM's article that we wrote up about the ABI. Following slide, a little bit more information about the instrumentation itself, or the data book from NASA. Go on to slide 64. And then following slide, we wrote a book up with different chapters about ABI, or about all it goes are space weather, ABI, lightning mapper, that was recently published. Go on to the next slide. So really, thank you so much for your time. Thank you for all who've contributed to this presentation. Thank you to the GOES program office, and that's their website there. If you go on to the following slide, again, thank you for your time. There's another link to that link of links with more information. And if we go on to the last slide, shows a composite of GOES 17 and 16, the number of hurricanes, again, that website. So I thank you so much for your time, and I'm ready to take any questions either now or later if they come via email, however you want to handle it.
All right. Okay, let's keep a big pause. Okay, we take kind of a short question from audience or from the online.
Hi, this is Shijian, and thank you very much for the great talk. I have a quick questions about the product air motion vector. And could you please comment or about the direction that for the low-level AMV products, what's the plan for improving, or is that a great improvement for the low-level AMV accuracy?
Yep. Yeah, no, that's a great question. So the question about the atmospheric motion vectors, they've been a mainstay of tracking, time components over the 3 time periods and being able to derive the atmospheric motion vector. I mean, I think the most exciting part, and there's been some research to use the mesoscale sectors. So instead of being tied to a 15 minutes or 30-minute cadence, you can get down to 1 or 2 or 3 minutes, whatever makes sense. There's been some preliminary research to show improvements with tropical cyclones using those mesoscale winds. So I think that's one big area of research. I think that we're learning more about how to assimilate the winds over time, and I think that combining these data sets together, there's some work with stereo, using the overlap between GO 16 and GO 17 or for other ones to get an improved height assignment. I think once we get a hyperspectral sounder up there too, that'll also help with the height assignment. As you know, that's one of the larger air of the atmospheric motion vector. I'll also say on that GOES-R webpage, there's a link to all the ATBDs, or algorithm theoretical basis documents, and there's one on their winds, and it's been recently updated as well. So that's where you can get a little bit more of the technical information.
Thank you very much.
You can advance the precipitation estimates, especially the extreme ones. So, here again, the ABI alone, really is just still looking at the top of the cloud. It can give you the time rate of change, which is important. How big maybe an anvil's growing over time. That information can be useful. But I really think the real best way to do it is combine it with the microwave data when you have it, and then use the GOES for the time evolution. And so not try to make an infrared only product, which isn't tightly as coupled with what you really want to know is the precipitation. I will say though that there is a lot more information about precipitation in the ABI than we had in the legacy, because now we have finer resolution in space, we have finer resolution in time, and we have some spectral bands. For example, I mentioned the 1.6 that can give you about the cloud top, is it glaciated or not? And you can use that to adjust your precipitation estimations. And there's also a algorithm theoretical basis document about precipitation on that GOES-R webpage. I will say, if any questions you think of later, my email is out there. Pass them to your professor there, and they'll get in contact with me. I'm always happy to answer questions about GOES, past, present, or future. Take a look at that web page. I guess maybe I don't have my email on there, but it's in the NOAA locator, or you can get at it via that web page there. So take a look there. It's an exciting time with not only the advanced baseline imager, but the ring of geo imagers, the AMI, with the similar spectral characteristics, although also including a green band. So I'm very, very jealous of that. So it's an exciting time to be involved with geostationary imaging. With your next generation of satellites in the GeoXO to be launched in the future, what are the main areas of improvements do you expect? I'll really break that up into the imager and other. So I think the imager is really going to be, there'll be some improvements, but there'll really be refinements. So, you know, it'll maybe have a couple extra spectral band, but, you know, just a few more. Again, most of the spectral bands will probably be at the same spatial resolution, but some, like I mentioned, the 4 micron might be at finer resolution. So I'd say that what the imager on the next generation is really a refinement. The big improvement comes with some of these new sensors. Specifically, I think the advanced or the advanced sounder, you know, to get more vertical information. Some of the other instruments they're looking at is a basically air quality sensor, you know, visible UV visible sensor to get a better idea of trace gases. And I think that's where some of these game changers will be, especially when we combine the information. The imager fused with or combined with the sounder, combined with, say, aerosol or trace gas sensors. So yes, I think it'll be data quality, but I think there'll be improvement there. And then how do we deal with the continuity problem through different satellites with long-term? That's a great question. It's hard to both have continuity and improvement, but that's why we're trying to have some of the, you know, similar, since ABI is a good instrument, just like AMI, that's why there'd just be some refinements there, but keep a number of the bands very similar in their characteristics. But sometimes it's, you know, instead of having, you know, we had 1 water vapor band on the previous legacy GOES, but being able to split that up into 3 water vapor bands, now we could get different levels of the atmosphere, more sensitive CO, SO2, etc. So you don't want to just do continuity, but it is that balance, and hopefully we're striking that the right balance.
Hello, Professor. You mentioned the hyperspectral sensor will be used on the new generation geostationary satellite in the future. Does NOAA consider that make an active sensor like a radar on board the new geostationary satellite in the future?
Yep. Yeah, thank you for that question. Also, thank you for the honorary degree, because I'm not actually a professor, but I appreciate that. So there will not be a radar or an active sensor on this next generation geostationary constellation. One other thing that was looked at was a microwave sensor, which might be possible, but really would need its own spacecraft and a large antenna. And again, so that was not deemed to be a deal. Again, remember this, you know, we're talking about operations. Ideally, some of those things could be demoed first and before they go on to an operational one. But the distance from geo is just really too far for an active radar type sensor like that. Thank you for your question.
Thank you.
Thanks, team.
All right. Well, thank you all for your time. As you can tell, I really enjoy talking about GOES. So again, if you think of any questions, you wake up tomorrow morning, oh my gosh, I thought of a question. It's not too late. Send them via email, and we're happy to talk about GOES past, present, and future. So you're welcome very much.
Sure. Do you mind, by the way, do you mind we post, share your slides on kind of Google Drive somewhere else to share with the local people? Yeah. Do you mind it?
No, I don't mind at all. Please share away.
Okay. So I may put your email address on such like the first slide, and so that people can contact you by email.
Yep. No, that's a good idea. I in hindsight, I should have done that. So
Okay.
yeah. So thank you for that. Well, you guys all enjoy your tomorrow.
Okay. Okay. Actually, we are morning. We are morning.
That's
we are
right.
in the morning. Yeah. Okay. We really enjoy the data from both Himawari 8 and Ghost 16 and even 17 right now. Actually, that's kind of to help us to more advanced and such like natural disaster mitigation locally. So we also appreciate all the effort done by Ghost R studies.
You are welcome. All right.
Okay.